Okay, we had left off in the previous video where we were talking about running this chi-square goodness of fit test. And this is typically a test that we're using on one population to try to measure whether a claimed distribution is correct or not. So the problem that we had left off on the previous video was this hockey problem, talking about the National Hockey League and whether the birthdays of these National Hockey League players were actually kind of evenly spread throughout the calendar year, so that they weren't given this unfair advantage of being born in January and kind of being almost a year older than some of their counterparts here. We had done the problem on the previous page, worked through all the steps, this Phantoms acronym here. And what I'd like to show you here today is how you can use the goodness of fit test on your calculator to run these problems. So what I'm going to do is, from the previous page here, I'm going to grab these observed counts that you see here. Those were the number of NHL hockey players that were observed to have birthdays January to March, April to June, etc. And then we had calculated that the expected counts is to really say that of those 80 NHL hockey players, that there really is no difference with whether you make it into the National Hockey League based on when you were born. And so we were just saying that even amounts of those 80 individuals, 20 would land in each of these different sections in the calendar here. So on the next page, what I have behind this box here is basically just a copy of those expected counts and the observed counts. And if you're going to run the chi-square goodness of fit test on your calculator, what you're going to need to do is you're going to need to input all of your observed values into L1, and you'll need to input all of your expected values into L2. And you can see off to the left, I've got some screen captures here and some steps that are essentially telling you that where you're putting the observed, where you're putting the expected. Okay? Calculator is going to look for data to have been typed into L1 and L2. Now, older calculators do not actually have the chi-square goodness of fit test in their calculator. You are allowed to then have a program on your older calculator that would basically run this test as well. So anyone that has an older calculator and doesn't have this test on it, I have a program that I can give you that will allow your calculator to run this as well. So what you're basically going to do, I'll go ahead and just flip to my calculator here. I have already preloaded my calculator with those observed counts and those expected counts. So you can see I've got those in L1 and L2. Okay, where we find all of our statistical tests is behind the stat button. We're going under the test menu, and you're just going to scroll down until you see that chi-squared value and then GOF test. That's our chi-square goodness of fit test. It's going to want you to tell it where did you put the observed counts, where did you put the expected counts. By default, I believe that already should be L1 and L2. And then it's going to want you to input the degrees of freedom. Now remember, the degrees of freedom has nothing to do with your sample size minus 1 when we're doing these chi-squared tests, but in fact, it's the number of categories minus 1. So on this particular problem, they kind of partitioned the calendar year into these different quarters. There were 4 different groups of months. So we had 4 categories. So our degrees of freedom should be 3. You can come on down. Usually I select the calculate as opposed to the draw menu. And you can see what I have on my screen here is exactly what I have on your notes page here that I have captured. If you choose the calculate menu, you can also see that if you were to choose the draw menu, it does give you the chi-squared test statistic value in the bottom left corner. It does also report the p-value, which is what we would want to use to compare to our alpha level so we can decide whether we're going to reject our null hypothesis or fail to reject it. Okay, I have highlighted in this box here that you always want to make sure that you are essentially reporting all of the values that are displayed on the screen. And so again, if you look at this middle screen here, I would always report the chi-squared value, the p-value, and the degrees of freedom. Now we're going to talk in just a moment about what this piece of information is right here, that CNTRB, that is short for contribution. But if we were to compare this p-value 0.01 to the alpha level of 0.05, we would definitely choose to reject the null hypothesis. And if I just flip back to the previous page, when we did this problem more by hand, you can see as well that we got the same chi-squared value by hand when we used the formula as we did when we used the goodness of fit test on the calculator. Also, very similar p-value, we would arrive at the same conclusion to reject that null hypothesis. So I think the key with anything in AP Stats is if you are going to utilize your calculator, you have to make sure that you are reporting the inputs and really the outputs that you're seeing there on your calculator. Okay, so a lot of times what happens with these chi-square tests is a problem will ask you to do what's called a follow-up analysis. And this is typically done when the results, meaning the results of your significance tests, are what we call statistically significant. And when we say that the results were statistically significant, that generally refers to the fact that the decision that you made at the end of running your SIG test was to reject the null hypothesis. So if you had enough convincing evidence to reject the null hypothesis in favor of the alternative hypothesis, that means your results were statistically significant, and the problem may then ask you to run this follow-up analysis. What this is wanting us to do is it wants us to try to determine which of the observed terms was contributing the most to the chi-square test statistic value. Okay, we know that when we get the chi-square test statistic value, we're taking the observed count minus the expected count, we square that, divide it by the expected, and then we keep adding those together, and the sum of all of that is what your chi-square test statistic is. This abbreviation, CNTRB, stands for contribution. So we're trying to figure out which of our observations, here is contributing the most. And what happens when you run this chi-square goodness of fit test on the calculator, automatically the contributions for each separate value are stored in a list called contrib, CNTRB. Obviously, the bigger the value means there was more disparity between what was observed and what was expected. Now, I'm just going to scroll back up here because you can see on that screenshot here that we were given a list of each of the contributions here. What I tend to like to do, and I'm just going to pull the calculator back up here, I like to kind of see my list of contributions next to the observed and expected values. So what I tend to do is I go into my list, stat edit. I move the cursor directly on top of L3, and I'm going to define list 3 as being the contribution values. Now to do that, you need your cursor here on top of L3. You're now going to press second and the stat button, and you can see there's our standard L1 through L6. Excuse me. But option 7 is that contribution variable. Okay, if you select that, you can see at the bottom here, it's wanting all the contributions to go into L3. If you press enter, then it puts them in there. You can kind of see them next to each of those observed counts. So I'm just going to go ahead and copy that down here at the bottom. I have my L1 and my L2. These are my contributions. The largest, the more the value is, that is the more disparity between what was observed and what was expected, which is creating a larger contribution to what that chi-squared test statistic is. And you can see that in this example, here's our largest contribution. And so what we might say for this problem is we could say, now remember, what was the 32? Well, the 32, I believe, was the observed count of birthdays for January through March. Okay, so we can make the statement, January through March birthdays contributed the most to the chi-square value. And then they often want you to remark by how much. Well, we can say that it's 12 more than what's expected. Okay, now where am I getting the 12 from? That's not really the 7.2. Remember, this is the observed, L2 is the expected. You can see I was expecting to only have 12 NHL players have birthdays between January and March, but what I actually observed is that there were 32. So that's where I'm getting this, there were 12 more than what I was anticipating there. Okay? This is always something that if you're doing a follow-up analysis and it wants to know which of the different categories contributed the most, always then at the end say, well, it was either this much more than expected or this much less than expected. So we're going to try to run through two more examples here together of this chi-square goodness of fit test. And when we get to the step where we're calculating the value of chi-squared and meeting the p-value, we're just going to use this feature on the calculator. Okay, so here's what we're looking at in this particular problem. I think this may even be a released question from a previous AP test. It says a study was conducted to determine where moose are found in a region containing a large burned area. A map of the study area was partitioned into the following 4 habitat types. Now, just to make sure this is clear what this map is showing us, I'm just going to kind of run the marker around where the burned area is. That section that I ran the marker around, that is this large burned area of land. Okay? Now, they're trying to track how frequently do these moose kind of return to each of or any of these different habitat types. And so here's what we're looking at. The section that's labeled a 1, you can tell that's obviously inside the burned area, but it's not out towards the edge of the burned area. Okay, it's kind of in the center there. The section labeled 2 is still also inside the burned area, but it is now near the edge. 3 is outside the burned area near the edge, and number 4 is outside the burned area, not near the edge. Okay. So it mentions that this figure is not drawn to scale, but it says the proportion of the total acreage of each of the habitats was determined for the study area. You can see this in this chart below. It says, using an aerial survey, moose locations were observed and classified into one of these 4 habitat types. So in other words, they are observing these moose maybe from a helicopter, and they notice that, hey, there were 25 moose that were kind of hanging around this habitat number 1 type area. And there were 22 that were in that section labeled with a 2 on the map. Now let's look at what the question is asking for. This is going to help us figure out what our hypotheses should look like that we're going to draft for this problem here. It says the researchers who are conducting the study expect that the number of moose observed in a habitat type to be proportional to the amount of acreage of that type. Now notice the total acreage of all of these habitat types is 1 complete acre. Okay? So they're trying to see if they're expecting that the number of moose that they're observing would be proportional to the amount of acreage. It says, are the data consistent with this expectation? conduct an appropriate statistical test to support your conclusion. Oh, and look at this last part here. It says, assume that the conditions for inference are met. If you ever read a problem that mentions to assume that the conditions are met, that means when you get to that step in the Phantom's acronym to list the conditions, that's the A there in the Phantom's acronym, you can simply remark, conditions are met, okay? Because that was given to us. All right, so I'm going to go ahead and label, I guess we have here, these are the observed counts. I'm going to go ahead and extend an extra column here for us to fill in the expected counts here. Okay, now you want to make sure that you're taking note how many total moves were observed. And we have 117 total moves observed. And so what we're looking at here is we're essentially saying that 0.34 acres out of 1 acre is 34%. If I'm expecting the observed moose to be proportional to the acreage, then I would expect 34% of the total 117 moose to be in that first habitat. So I would multiply those numbers together. Remember, we never round the expected counts. So I'm going to write down that I'm expecting 39.78 moose. And then I'm just going to keep going through, and I'm going to take this. This was really easy because the total acreage was just 1. They made that easy for us. So we're basically taking 10.1% of the 117 moose, and that gives us the expected number of moose that we would see here. So I'm going to go ahead and fill in the expected number of moose here for each of these values. You can see that this should all total as well to 117. Okay. All right, so let's go ahead and start our process here. The Phantom's acronym, of course, we don't actually have anything for the P. We're not doing anything with a parameter, proportion, or mean here at all. But we do want to list what our null and our alternative hypotheses are. Okay, so the null hypothesis would simply be that the number of moose in each habitat is proportional to the acreage in that habitat. Okay, and then our alternative is essentially that same statement, but that it's not proportional. Okay, so we have to write all of this out again. I know this is tedious to write this. There's a lot of writing involved when we're running these hypothesis tests here. Okay, so here we're going to say it's not proportional to the acreage in that habitat. Okay, the other thing we want to include in this H step is if they did not give us a significance level, we're going to go with our default 0.05. Okay, here we are for our assumptions. We are going to just, as they told us, we are going to assume that conditions are met. And we don't need to do anything with random or showing that the expected counts are all at least 5, which we can see that that is the case. Okay, the N, we're going to list for the N here. This is us naming the test. The test is the chi-square goodness of fit test. Okay, and that brings us down to the T in Phantoms. The T and actually the O are both when we are saying the value of the test statistic, the chi-squared value, and the O is us obtaining the p-value there. Okay, now we're going to need to write down a few other things here, but let's go ahead and go to the calculator. Okay, and on the calculator here, I'm going to need to clear out what I have here in my list. Okay, and we're going to go ahead in L1 and put our observed counts, and then the expected counts here in L2. Again, I'm just making sure that we're putting the decimals. Okay, I got those in. I think those are right. I'm going to press stat, test, going down to goodness of fit test. Now, degrees of freedom. This is actually something I should be writing down here somewhere on my paper. The graders are going to want to see what I'm saying the degrees of freedom are. There were 4 habitat types. There's 4 categories here. We should do one less than that for our degrees of freedom. We're going to come down, punch the calculate menu, and we need to report a few things here from our screen. Our chi-square value, you can round it to 2 places, is fine. 43.69 here. Now be careful with this p-value. It's in scientific notation because you see that e to the -9, which essentially means that if we moved that decimal point 9 places to the left, the number would be so small it is virtually 0. And so we can essentially report 0 here for our p-value. Okay, now it's time for us to make a decision. So always when you make your decision, you always are comparing your p-value to your alpha level. If it's less than that, our decision is to reject the null hypothesis. And finally, we're going to state our conclusion. If we're rejecting the null hypothesis, we are going to say that we have convincing evidence that, remember what comes after this? It is you looking back up in the problem and simply rewriting your alternative hypothesis, which is that the number of moose in each habitat is not proportional to the acreage in that habitat. Okay, I hope that you take the time here. If you need to pause the video, you can, but it is important that at least on some of these examples, you are going through the process on your calculator where you're putting the values in L1, in L2, and running this yourself, just to make sure that your calculator is running properly here. So we have what you see on this last page here, that we're going to stop once we do this last example. You can see over here on the right is this process for running the chi-square goodness of fit test. If you weren't going to use that feature on your calculator, but say you had your chi-squared value and you wanted to find the p-value a different way, you could use this chi-squared CDF, which I think I may have mentioned that in the previous video. Remember, your chi-squared curves are always skewed to the right, so your chi-squared value is always the lower bound, and your 10,000 should always be the upper bound, and then your third input is just the degrees of freedom. That will give you the p-value. I would think most people would just run the goodness of fit test straight from the calculator, but that does give you the p-value as well. So let's do one last problem here. This is looking at, instead of plain M&Ms, we're looking at peanut M&Ms. You can see that the company is reporting the color distribution to be 23% for blue and orange, etc. It says Joey bought a randomly selected bag of peanut M&Ms. He counted the colors of the candy in his sample. Here's the results. Okay, what conclusion can you draw about the company's claimed color distribution? Okay, so I'm going to go ahead and draft my 2 hypotheses first, and then we'll go back and do our observed and our expected counts. Okay, we're going to say here that the null hypothesis is simply that the company's claimed color distribution is correct. And then our alternative is that the company's claimed color distribution is not correct. Okay. Also going to just state that our alpha level will be 0.05. I'm going to make a little chart over here for observed and expected. we do have 6 colors here. So we need to write each of these separately here. Green, we got yellow, red, and brown. Oh, sorry. Okay, well, I should have given myself a little bit more space there because I need to write the observed counts next to those, but I guess I needed to distinguish the colors here anyhow. Okay, good enough. I have room here. I think that there were 12. I'm getting these right from this right here. These are the observed counts. 12 blue, 7 orange. Okay, I'm just going to squeeze these numbers right in there. Okay, and then to get the expected counts, this is where we're using these claimed percentages. Okay, now this is where we need to know what was the total number in his sample. Okay, when Joey took this sample, we need the total so we can make these proportions correct. Total number of M&Ms in this sample were 46. So I'm going to go back and calculate 23% of 46, and I would get 10.58. So I should be expecting 10.58 of both blue and orange. 15% of 46 would be roughly 6.9 for green and yellow, and 12% of 46 is 5.52 for the red and the brown. Okay. All right, now it doesn't say anything here on this problem about assuming conditions are met. So we do have to run through our conditions here. Our 3 conditions that we'll need to make statements or remarks about are randomness, 10% condition, and then the large counts condition. Okay. All right, so it does mention up above, I believe that Joey did take a random sample. So bag selected randomly, you can say. The 10% condition, 10 times the sample size, that was 46, should be less than or equal to, I don't have, oops, go ahead and fill in what this is here. That's 460, I should say equals here, sorry. 460 needs to be less than or equal to all peanut M&Ms. There's definitely a lot more than 460 peanut M&Ms here, so we're well below the population size. In our large counts condition, we need to make a remark here that all the expected counts are greater than or equal to 5. Okay? I can draw an arrow here, or I could list, there's really just 3 types of expected counts, 10.58, 6.9, 5.52. Okay, I'm going to name the test. This is the chi-square goodness of fit test. Okay, and then we are ready from the calculator to see if we can pull the value of chi-squared. I'm going to need to put in degrees of freedom, and then also the p-value. Now, we have a lot more than just 4 categories here. There's 6 colors, so our degrees of freedom on this is going to be 5. Let's go ahead here and put our data into the calculator here for this last one. Okay, we're going to put in the observed counts. Oh, I missed something. Okay. And L2 are our expected counts. Okay, I'm going to go ahead and press Stat Test. I need to change my degrees of freedom to 5. Okay, and then I'm going to go ahead and report the chi-square test statistic as 11.37. The p-value will be 0.04. So the decision that I'm going to be making here is I'm going to say since the p-value of 0.05 is less than the alpha, I'm sorry, 0.04 is less than the alpha level of 0.05, we will reject the null hypothesis. And we can say we have or there is convincing evidence that, I'm going to state our alternative hypothesis here. The company's claimed color distribution is not, that's our alternative, not correct. Okay, last part to this. It says, which color contributed the most to the chi-square value? So I'm going to just hop back on the calculator here. I'm going to go into Stat Edit, move the cursor on top of L3, press second Stat, and select that contribution command here. Whatever the largest value is here, this is what would have contributed the most. I'm seeing 5.39. That's my third value down. Okay, so as I look at the third value down, that is referring to the color green. Okay, so green contributed the most, and then I want to say how many more were observed than what was expected, or how many less were observed than expected. So I would say down at the bottom of the paper here, I'm just going to write it right here so I don't have to scroll. I'm going to say green contributed the most. It was, and it looks like whatever the difference there between 13 and 6.9, it was 6.10 more than expected. Okay? That's called a follow-up analysis. Okay, that brings this video to a close. There's a few problems there you can go ahead and try for homework.